Hello everyone, this is chapter 11, Analysis of Variance. In this chapter, we will cover an overview of ANOVA, one-factor ANOVA, multiple comparisons, and touch upon tests for homogeneity of variances. Right? First, an overview of ANOVA. What is ANOVA? ANOVA stands for Analysis of Variance. It is a comparison of means. Basically, the ANOVA allows you to compare more than two means simultaneously, like three or more means, simultaneously. Proper experimental design efficiently uses limited data to draw the strongest possible inferences through ANOVA. And so, what does ANOVA do? ANOVA do for you? Well, what's the goal of ANOVA? How does ANOVA work? Basically, the goal here is to explain the variations. ANOVA seeks to identify sources of variation in the numerical dependent variable y, also known as the response variable. The variation in y about its mean explained by one or more categorical independent variables, or they're called the factors, or it is what is unexplained ones. That's the random error. So in this equation, you can see the variations in y, the dependent variable around its mean, can be analyzed into two parts, or split into two parts. One part that's explained, and the other unexplained. The explained part is due to the factors, the independent variables, and the unexplained part is due to random error. There's not much we can do about the random error, but we can use ANOVA to analyze those factors that contributed to the variation. The goal, each possible value of a factor or combination of factor is a treatment. Right? And we test to see if each factor has a significant effect on y using, for example, the hypothesis like this. So H null in this case is mu equals mu1. Sorry, H null is mu1 equals mu2 equals mu3 and equals mu4. That is the mean of the dependent variable, under different treatment. And H1 is that not all means are unequal. So at least one of them is not the same. It's not equaling to others. Okay? And the distribution, the test of this ANOVA uses the F distribution. F distribution will show you in just a minute. Okay? And if we cannot reject null, we conclude that observation within each treatment have a common mean of mu. So we want to see if mu's are the same or not. Right? This chart summarizes a one-factor ANOVA, and in this case, it's about the defect rate of a plant. A company with different plants, 4 different plants here, A1 through A4. A1 is Lee's Bluff, A2 Cacton, A3 Johnston, and A4 Goriswell. They have 4 different plant locations, and each location, they're all turning out, the same, same parts for the company. Now, what about defect rate? Are the defect rates at each and every location the same? Are they the same or not? Or in other words, is one factory location, plant location, doing better or worse than other factory locations or plant locations? So the defect rate here, y, is a dependent variable, is numerical, and that may be affected by, we're speculating, by one of the independent variable. One independent variable that is categorical in this case is just plant location. Right? This will be an example of a one-factor ANOVA. This is a dependent variable. These are the factors. For example, a one-factor ANOVA would test the hypothesis that the length of a hospital stay, or LOS, is affected by type of fracture. The length of stay is a function of type of fracture. In this example, we know that patients go to hospitals for the fractures in their bones. And how long do they stay? Right? The length of stay, hospital stay, or LOS, that's a dependent variable. Now that variable depends on type of fractures the patients have. Maybe it's the hip bone or a head bone or other bone, a different type of bones. Then we can also look at this through a two-factor ANOVA. Two-factor ANOVA. That is, we can test the hypothesis that the length of hospital stay, or LOS, is affected by both type of fractures and age group. As we can imagine, maybe younger people will recover sooner, faster than older people. So the length of hospital stay, how long people stay, patient stays in hospital, is a function of two factors. One is the type of fracture of the bone, and the other is age group. And also we can test for interaction between the two factors. And maybe for elderly people suffering from hip bone, requires a longer stay than a young person suffer from, let's say, an arm fracture, leg bone fracture, for example. Okay. This table here, table here, gives you a summary of one-factor versus two-factor ANOVA. In one-factor ANOVA, dependent variable is what hospital stay. We have seen that affected by the independent factor variable of type of fractures. The type of fractures could be facial, A1 facial bone fracture, A2 radius or ulnar fracture, and number A3 hip bone or femur fractures, A4 other lower extremity fractures, and A5 all other fractures. And there are 5 factors here that affect the length of hospital stay for the patient. That's one-factor ANOVA, because it's only one factor, which is factor A, type of fracture. Or if you want to look at this, the same case with two factors, one factor is still the factor A, type of fractures, and then factor B will be the age group. Right? So the length of hospital stay could be affected by two independent variables. One is factor A, same different type of fractures. And the second by factor B, that is B1, B2, 3. B1 for people under age of 18. B2 is from 18 to 64, and B3 for 65 and over. Right? So this would be a two-factor ANOVA. There are some assumptions in ANOVA. Analysis variance of ANOVA assumes that the observation on Y are independent. In other words, for example, the defect rate at different plant locations are independent of each other. And how long a person may stay in a hospital, from one person to another, they're also independent. We can expect that. We can also assume that. And populations being sampled are normal. That's the second assumption. Right? Population being sampled have equal variances. The variances must be the same for the whole population, for the being sample, for the sample to be to draw from those populations. Okay? And also we have noted that ANOVA is somewhat robust to departures from normality and equivariance assumptions. So if it's not totally exactly following a normal distribution, then ANOVA is still a good solution. If the variance is not exactly the same, ANOVA can still work. Okay. Calculation of ANOVA. We can use software such as Excel spreadsheet or Megastat and Minitab or SPSS software to use to analyze the data. And large samples increase the power of the test, we can see. But the power also depends on the degree of variation in Y. Lowest power would be in a small sample with high variation in Y, and that would be the really bad situation. Right? Data format. If you use an Excel or use some software, a one-factor ANOVA only compares the means of C groups. C is the number of groups, treatment groups, or factor levels. Consider the format for one-factor ANOVA with C treatments denoted as A1, A2, A3, and AC. Right? You can have the data in columns, one-factor ANOVA data in columns like this. So this would be the factor A1, that's first treatment type, and then you have observation Y11, Y21, Y11, Y21, Y31, etc. That's their total of N1 observations. For treatment number 2, the second treatment, you have Y12, Y22, Y32, all the way to the last one. So there are N2 observations. For the last factor, factor treatment type CAC, we have Y1C, Y2C, 3C, etc. The NC, that's the number of observations. You can also have the data in rows, as A1 through AC, not in columns, but in rows, that's also fine. You just have to tell the software, the data are in rows or in columns. Data format, also continue on data format. Sample sizes within each treatment do not need to be equal. That is balanced. In other words, for the first treatment, you may have an N1 number of observations, but for second treatment, you can have N2. N1 and N2 do not have to be equal. But total number of observations, of course, or total number of observations, N equals N1, that's the number of observations in first group, plus N2 number of the observations in second group, and all the way to the C, the last group. Right? So in ANOVA, the hypothesis to be tested is H0 is mu1, that's the dependent variable, the value of that, Y variable for the first treatment equals mu2 equals mu3, mu4, mu5, mu6, all the way to mu C. And C is the number of groups. And an alternative hypothesis is that not all the means are equal. At least one of them is not equal. Then the ANOVA tests all means simultaneously, so does not inflate the type 1 error. Okay? We can also look at a one-factor ANOVA as a linear model. That's an equivalent way to express the one-factor model is to say that the treatment J, right, came from a population with a common mean plus the treatment effect AJ plus random error. So for this dependent variable Y, right, its values comes from the common mean of mu plus a factor of A, that's the treatment effect. Because of a different treatment, because of different plant locations, because of different bone fracture types, or because of different age groups that patients comes from. These all have impact on the mean, and then that will affect value of the mean of the dependent variable Y. Okay? And of course, there's always this error term that we cannot avoid. So J equals 1, 2, 3, 4, all the way to C. The C is the number of treatments we can have. Right? And I equals 1 through N. That's the total number of observations. Random error is assumed to be normally distributed with zero means and same variance for all treatments. That's one of the assumptions. So ANOVA can be expressed as a linear model. Okay. When ANOVA is expressed as a linear model, the fixed effect model can only looks at what happens to the response of a particular level of the factor. That is, we're testing to see if A1, that's the response from the first factor, equals A2, A3, A4, A0, all the way, or they all equal to 0. means if there's no effect from those factors, then that's the actual normal state, assumed state. H1, the alternative is hypothesis, not all ages are 0. If one of them is not 0, then it's going to have impact on the mean, on the dependent variable. So if H0 is true, then the ANOVA models collapses to y equals mu plus the error. So that is the effect from the treatments are not there, non-existent. Okay. And in calculating ANOVA, when we use a completely randomized design, we can calculate the means of each group, each treatment group. The mean of each treatment group is y bar j equals the sum of all the elements, all the values in the group divided by total number of groups, numbers within that group. So that is the mean of each group. And then what is the overall sample mean? The grand mean then. The grand mean can be expressed as the sum of all the group means over the total all the treatment categories. Right? So you for every individual y number observation, you add up from 1 through j for its mean for all its values within the group, plus we add up from j equals 1 through c for all the different treatment groups divided by the total number of n. Right? We can short this, express this as y nj times y j bar. That's right here. Okay. So that's the overall sample mean of the all population of all the population items. How do we actually do the one factor ANOVA? We actually do this by partitioning the sum of squares. For given observation, in each observation yij, that's ith column, ith row in jth column, excuse me. The following relationship must hold true. Okay, yij minus y bar, that's the that's the individual y item value minus its overall mean must equal yj bar times minus y bar mean plus yij minus yj bar. Why is this equation holding true? Because if you open the parentheses, what do you see? You see that this item here, yj bar, and this item here, yj bar, cancels each other. What we have is just yij minus y bar. That's exactly what this is. Right? But the reason why do we partition the separate the sum of squares? We do that because this yij minus y bar. Excuse me, there's something wrong with this slides. This should be y bar here on top. Okay. This is actually the deviation of an observation from its grand mean. This is the observation of individual observation, and the y bar the bar on top is the grand mean. So this is a deviation of an observation from the grand mean. So this item here, and this item here, yj bar minus y bar, that's actually the deviation of the column mean from the grand mean. Right? This is a deviation from the column mean right here, column mean from the grand mean. And this actually shows the effects of different treatment groups because each column represents a different treatment. So this is called between treatments, this part. This part is actually deviation yij minus yj bar. That's a deviation of the observation from its own column means. Right? This is column means, right? This is individual observation. So that deviation is actually due to variations within the same treatment group. So we call that within treatment. So there is a between treatment part, there is a within treatment part in a total deviation. Right? Now why are we doing that? We're doing that because this relationship is also holding true for sum of squared deviations. then therefore yielding partitioned sum of squares. So the sum of squares yij minus y bar is squared. This sum of squares also, holding true that we can also write this sum of squares here into two parts. This part here is between groups, and this part here is within treatment groups. If we put simply, if this is actually sum square total, right? That from individual observation to its grand mean, we call it sum square total, or SST. SST, or sum of square total, equals SSA plus SSE. This is SSA right here. This is SSA. That's sum of squares of between treatments. That's the part that's explained by factor A. And this part here is sum of squares error. That is sum of square within treatments, that is SSE, unexplained, that's due to random error. Okay, so SST, sum square total, equals SSA, sum square between treatments or due to treatments, and plus sum square error. Okay, that's for ANOVA. And then what do we do that? For F-test, it's actually we need the mean squares. SSA and SSE are used to test the hypothesis of equal treatment means by dividing each sum of squares by its degree of freedom to adjust for group size. So these ratios are called the mean squares. Mean squares, or mean square A, MSA, and mean square error, MSE. And then the F statistic, as we know, ANOVA is the F-test. The F-test statistic, in this case, is mean square A, MSA, divided by MSE. That's how we calculate the test statistic for F-test of ANOVA. Okay? This actually gives you a good summary of the calculations for ANOVA, one-factor ANOVA. Because you have SSA, that's a between groups treatment sum of squares. And then you have within group error, the sum of square error, SSE, SSA, SSE. You add these two together, you get SST, sum of square total. Okay? And the degree of freedom for SSA is C minus 1. C is the number for treatment groups you can have, or treatment categories you can have. And then N minus 1, N is total number of observations. N minus 1 is the degree of freedom for sum of square total. For sum of square error, the degrees of freedom is N minus C. And you can see that C minus 1, this one here, degree of freedom between groups, plus degrees of freedom within groups, this plus this will equal N minus 1. You can see that because the C cancels each other, so all you have left is N minus 1. So that's exactly what this is. Then how do you calculate the mean square? The mean square of between groups is SSA, this SSA here, divided by its degree of freedom of C1, C minus 1. And mean square of error is SSE, sum of square error within group, sum of square error, divided by its own degrees of freedom of N minus C. So that's MSE. You have MSA and MSE, and then you can calculate your F statistic. That is MSA over MSE, the ratio of that. Okay? And then we are ready to test. Right? If you use the Excel, one-factor ANOVA Excel, you can choose data analysis, and then Excel will show you the tools. You can go to ANOVA, single factor, click OK, then you'll be able to continue to perform ANOVA using Excel. Okay. Now the test statistic. We know the F distribution describes the ratio of two variances, right? MSE and MSE. Right? The F statistic is the ratio of variance due to treatments, that's MSA, to the variance due to error, that's MSE. So MSA over MSE is the F statistic. MSA equals SSA over C minus 1. The degree of freedom is of 1 is C minus 1. That's the numerator degree of freedom, C minus 1. For MSE is SSE over N minus C. the degree of freedom of which, or df2, degree of freedom 2, is n minus c. That is the denominator degrees of freedom. So you need 2 degrees of freedom, to find the f, critical value of f. Okay. Then when f is near 0, then there's a little difference among treatments, and we will not expect to reject the hypothesis of equal treatment means. So how do we make decision in f-test, ANOVA? F cannot be negative and has no upper limit. Right? For ANOVA, the f-test is a right tail test. Tail is to the right. And we can use appendix F or Excel to obtain the critical value of f for given alpha. You can look at, now at this moment you can pause and go to your textbook, and in the back you will see appendix F. You will see the F table, which gives you the critical value of f. Okay. Again, as said, the f test is the right tail test. Okay. The long tail is to the right, and for a given alpha level, normally it's 5%, so it's 95% of alpha equals 0.05, and you find your critical value, right? And then if your test statistic, the F test statistics, falls in this region, we reject null. If it falls in this region, we do not reject null. That's how we do the ANOVA. Okay. So the steps in performing a one-factor ANOVA: the first step is you state the hypothesis. The H null is mu1 equals mu2, the odd way equals mu c. H1 is not always means equal, right? And then step 2 is state the decision rule. Right? You find the degrees of freedom for the critical value of f. Right? The numerator degree of freedom, or df1, is c minus 1. C is the number of treatment groups. That's between treatments. Denominator degree of freedom is n minus c. N is total number of sample sites minus groups. So that is within treatment groups. For the given alpha, you can obtain a critical value from appendix F, or you can get that from Excel. Okay. This is the appendix F in the back of your book, shows critical value of f of 0.95. In this case, let's say if this is the right here, if the degree of freedom is in this case is 16 and 3, right? And then we can have this critical is 3.24, right? At the 95% confidence level, right? So for critical value of f is 3.24, and that's if it's your calculate f statistic is larger. This is the denominator degree of freedom. This is the numerator degree of freedom from 1 through 12. This is denominator degree of freedom from 1 to 20 here. Okay, and if your f test statistics falls in this region, if it's larger than 3.24, you reject null. If it's less than 3.24, you fail to reject null. Okay. And if you use Excel to perform the calculations, this is the summary table, the results table you can get from Excel's ANOVA in Excel. Right? It's a simple factor ANOVA, right? And there's for the factors are four stations, and each has 5 observations, and this shows the sum of all the y-dependent variables from each station. You see they're different. This is the average from each different stations, and this is the variance. And then Excel calculated this statistic for you. In this case, between group sum of square, total sum of squares, between group sum of squares 1479.2, within groups 1914. The sum of square total, SST is 3393.2. The degree of freedom here for the between group is 3. This is because you have 4 groups. 4 minus 1 gives you 3. And also there are 4 groups with 5 counts each. You have 20 observations. 20 minus 1, n minus 1 or 20 minus 1 give you 19. That's for the total degree freedom of total degrees freedom. And then then you can calculate you can calculate either way. N minus c, that's 20 minus 4 give you 16, or you can use 19 minus 3 to give you 16. Either way. Then you need to calculate the mean squares. MSA. MSA equals this 1479 divided by 3 will give you 493.0667. MSE is you use 1914 divided by 16 give you 119.625. And how do you get the F statistics? Using MSA 493 divided by 119 will give you 4.121769. Okay, and the F critical is what we already know from the table. F critical and 5% is 3.2388. Okay, since your calculated F statistics 4.12 is larger than F critical, therefore we know you can reject null. Or alternatively, we know the p-value. We're using the p-value approach. We know the p-value probability here is 0.02, which is less than 0.05. We can also reject null. Okay. So step 4 is make the decision. Reject null if critical value ever exceeds the test statistic, or if the p-value is less than alpha, as we have seen. Megastat and Minitab can also be used to perform ANOVA, just the same. Okay. And from this part on, it's just optional. We will not test you. I'm not going to test you on this. You're not required to study this. Just you can study, continue study, just for your own knowledge, but you will not be tested on this. Basically, what we're saying here is, after rejecting the null hypothesis of equal means, we naturally want to know which means differ significantly. Right? We just know they're different, but which one differs? In order to maintain the desired overall probability of type 1 error, a simultaneous confidence interval for the difference of means must be obtained. For C groups, there are C times C minus 1 distinct pairs of means to be compared. These type of comparisons are called multiple comparison tests. Okay? One of them is the Tukey's test. Tukey's studentized range test, or HSD, for honestly significant difference test, is a multiple comparison test that has good power and is widely used. It's named after statistician John Wilder Tukey from 1915 to 2000. This test is not available in Excel's tools data analysis, but is available in Megastat, Tukey's test. Okay. In Tukey's test, there's a two-tail test for equality of paired means from C groups compared simultaneously. The hypotheses are the H mu j equals mu k between the two groups. H1 is they're not equal, so that's a two-tail test. Right? In Tukey's test, the decision rule is you reject null if the calculated t equals yj bar, the mean, minus yk bar divided by MSE and 1 over nj plus 1 over nk. Right? And if it's larger than t critical, then you reject null, where t alpha equals 0.707 times QCNC, and QCNC is a critical value of studentized range for the desired alpha. Okay? This is the two key test table here. For example, here's the upper 5% of studentized range. This is the number of groups. This is the number n minus c. This is C and n minus c. Okay. ANOVA assumption. We know ANOVA assumption assumes that ANOVA assumes that the observations are on the response variable are from normally distributed populations that have the same variance, right? And the one factor ANOVA test is only slightly affected by inequality of variance when group sizes are equal. So the test is test assumption of homogeneous variances. We can use Hartley's test, right? Hartley's Fmax test. In this test, Hartley's Fmax test, is named after H.O. Hartley from 1912 to 1980. This is the hypothesis about the variance being equal, and not all sigmas are equal. Right? The test statistics is the ratio of the largest sample variance to the smallest variance. Smallest, largest one, smallest one, the standard deviation squared, that's variance. Right? And the Hartley's F-test is a numerator degree of freedom, denominator degree of freedom, and this shows the critical value at 5%. Okay? And there's also the Levin's test. Levin's test is a more robust alternative to Hartley's test. Levin's test does not assume a normal distribution. It's based on the distance of the two observations from the mean for sample medians rather than from the sample means. It's from the medians. Right? A computer program, Minitabs needed to perform this test. We're not going to cover that. Okay? And so that concludes chapter 11.